Okay, as of right now, I'm going to say we're finished with functions. We're going to move on with our life, and we're going to go on to factoring. And I know it's like, why are we going to factoring? Well, there's one thing about factoring that we have not talked about, which was factoring perfect cubes. And we've talked about difference of two squares. We've talked about perfect square trinomials, but we have not talked about factoring perfect cubes. So I'm going to go over that strategy today because it's going to apply to what we're going to get into, because it's going to some of the work, or a lot of the work I should say, is going to involve a factoring component where you guys are going to be expected to factor the numerator, the denominator, or both, and cancel stuff out. And you're going to have to be able to do that. And getting it down to factored into its simplest factored form, that's what you want to do. Okay, so let's focus on this right here. I'm going to go ahead and just jump right into the setup for the sum of cubes and the difference of cubes. The sum of two cubes is where you have one cube, like, no, I'm not talking literally about like a cube or a Rubik's Cube. I'm talking about numbers that are cubes. So like 8 is a cube because that's 2 to the third power. 64 is a cube because that's 4 to the third power. That's 4 times 4 times 4. That's why it's called a cube. That's why it's called a perfect cube, because you're multiplying by 4 over and over again. 125 is a perfect cube because that's 5 times 5 times 5. That's 5 to the third power. Okay, so that's what I'm talking about with cubes. So we've got one cube added to another cube. Now the format, like I said, the setup for these problems, you're going to want to have these down. You're going to want to use these notes, kind of have these out, especially when you're working on these problems. So the format of this is going to be this. And I'll explain this in just a bit. Okay, so right here we've got A plus B, and then that's one binomial right there. And then you're going to have a trinomial in parentheses. You're going to take the A and you're going to square it. You're going to take A and B and multiply it. And you're going to put a subtraction sign in front of it. And then you're going to take the B term and you're going to square it. And I'll talk about what that really means once we start jumping into these. But it's going to be really important for you to kind of give you guys some heads up. It's going to be really important for you guys to figure out what A and B equal before you get down to doing all this. And I know you're like, what is A and B? But we'll get into that. All right. So that's a sum right there. We just did. That is a sum of two cubes. That's how you set it up, at least. I wouldn't call that a formula because, formula kind of derives an answer like, square feet or volume or surface area or something like that. But this is more of like the setup for how sum or differences of cubes is set up. The difference of two cubes is going to be set up like this. You're going to take the A and then you're going to subtract the lone B. That's your binomial. And then your trinomial is going to be very similar to what you had above, but it's going to be A squared plus A times B plus B squared. So they look very, very similar to each other, but it's going to be very important you guys have that written down so you guys can see what's going on there. And like I said, in order for you to solve these, you're going to need to know what A is, you're going to need to know what B is. Now, it doesn't hurt here to talk about like a list of cubes and just kind of go through some of them. I know some of you probably already have these committed to memory, but like 1 cubed is 1. 2 cubed just means 2 times 2 times 2, which is 8. 3 cubed just means 3 times 3 times 3. So 27 is a perfect cube. 4 cubed is 4 times 4 times 4, which is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is going to be 343, a palindrome. 8 cubed is going to be 512. 9 cubed is going to be 729. And 10 cubed, do you know what that is off the top of your head? It's 10 times 10 times 10, which is 1,000. So 1,000 is a perfect cube. And they keep going. I'm not going to list off all the cubes there are because that would take at least a couple minutes if I did that, or more, I'm not sure. But that would be a pretty hefty task. So that's a list of cubes. But here, more importantly, that's how numbers work. 1 is a perfect cube, 8 is a perfect cube by themselves. Those numbers by themselves are perfect cubes. But let's talk about exponentially. Let's talk about exponents. Now, exponents follow a different rule for cubes. Let's see if you guys can figure out what I'm doing here. All right, so if we have, if I'm talking about perfect cubes, all right, n to the third power is a perfect cube. All right, and we'll talk about like what the cube root is of that. I should probably write it like this. Let's put a 3 right there in the index. Okay, so maybe at this point you're kind of getting what's going on there. You're catching my drift as to what makes exponents perfect cubes. Because it's obvious that a lot of these numbers are not perfect cubes. 6 is not a perfect cube. There's no number times itself that equals 6. There's no number times itself that equals 18. There's no number times itself 3 times, I should say. There's no number times itself 3 times that equals 21. There's no number times itself 3 times that equals 24. Okay, but what you might notice is that the exponents, in order for an exponent to be a perfect cube, it just needs to be a multiple of 3. So if you have multiples of 3 right in there, if you have multiples of 3, then exponentially we're talking about perfect cubes. All right, so the cube root of n is going to be 3 divided by 3, which is just going to be n to the first. You don't need to necessarily show the 1 when it's got a power of 1, but it's there. 6 divided by 3 is 2. And just to kind of make a point of why is n to the 6, why is that equal to n squared? Well, let's cube that. Well, n squared times n squared times n squared equals n to the 6, right? Because we're using that product rule. The product rule states that we add those powers, right? We add the 2 plus 2 plus 2, which is going to be 6. So the cube root of 9 is going to be n to the third. I should say the cube root of n to the 9th is n to the third. The cube root of n to the 12th is going to be n to the 4th. And I know this is a pretty easy pattern to kind of figure out what's going on here. So as long as you divide those exponents by 3, and they're divisible by 3, and they're multiples by 3, then you're going to get the exponential cube root. Exponential cube roots are different than actual just numbers. The numbers like 8 is a perfect cube because it's 2 times 2 times 2. That works that way. 9 times 9 times 9 is 729. Okay, so let's jump into our examples here, and this is where it's going to start to kind of come together for you. So what I want you to do, all right, is understand our first term is going to be our a, and what we want to do is we want to find the cube root. We want to find the cube root of x to the third, because that will equal our a. So our cube root of x to the third is going to be x. And our cube root of 8 is going to be 2. So what we just found there, put you in on what we're doing right here, we found our a. Our a is equal to x. I know that's kind of a weird way to say it, like why isn't a just a? But a is equal to x, because we're talking about x cubed. We're not talking about a cubed. So it's x cubed. And our b is equal to 2. So those are our cube roots, in a sense. Those are the cube roots right there. All right, and then this is where it comes in handy if you write it all out. Now this is a sum of 2 cubes, so I'm going to write it like this. Okay, now it just becomes a matter of you kind of filling it all out and putting everything where it's supposed to go. Okay, so a is equal to x. B is 2. So I'm going to write, instead of a plus b, I'm going to write x plus 2, because a is x and b is 2. Now this one right here, this says a squared. Now a squared, that does not mean a times 2. That means x squared, because that's what our a is. Our a is x, so a squared is going to be x squared. Now AB, that means the product of A and B. So A times B. Now A times B is X times 2. That's an ugly way to write an expression. You always write the coefficient first and then X. So we're going to write minus 2X. And then plus the B term squared. Now the B is 2, so 2 squared is 4. So what we have here is, and this is as far as you're going to go in terms of the lesson here. That's all we needed to do because this is completely factored. We have factored that all the way. All right, I know it looks like another math problem. That's as far as we can go with that particular one. Okay, so let's go on to example B here and let's find some cube root. All right, so the cube root of x cubed, that's going to equal our A. And our cube root of 27 y to the 6th. Now there's a little bit more to that. That's going to equal our b. So let's go ahead and do this. So our cube root of x cubed is going to be x. So just like on the last one, a is going to equal x. Our cube root, now let's kind of break this up a little bit. Our cube root of 27, well 27 is 3 times 3 times 3. So the cube root of 27 by itself is going to be 3. And then we have an exponent. Now remember, exponents we treat differently. We're going to divide those by 3 to figure out the exponential cube root. So the exponential cube root of 6 is going to be 2. So that's what you get. So you get 3y squared. So what you want to do is you want to do like 3y squared times 3y squared times 3y squared. Well, 3 times 3 times 3 is 27. Y squared times y squared times y squared is y to the 6th. So that all checks out right there. So I would say this step that we're doing right here, figuring out what your A and your B, very, very important for you guys to get that right. Otherwise, I mean, that's kind of true in everything in math, but if you don't get these numbers, if you make a mistake anywhere in one of your steps, it's going to screw it up. But it's essential that you know what your A and your B are, for sure. Now this is a difference of 2 cubes. DOTC, that's a difference of 2 cubes because we have subtraction sign. So if it's a difference of 2 cubes, we're not going to do A plus B, we're going to do A minus B. And then the trinomial is going to be A squared plus AB plus B squared. And then this is where it comes down to you just being able to fill in the parts. Now according to the cube roots we just got, well A is X. Our B is 3y squared. So I'm going to write minus 3y squared. Next, we're going to do a squared, and well, that's going to be x squared. And then AB means a times b. So it's just we're just going to put all that together. So we're going to write plus 3xy squared. Now, if you wrote x squared y, or if you wrote y squared x, is that okay? Yeah, it's fine. It's just a lot of times in algebra, we kind of put things alphabetically, right? And then for b squared, we're going to take this and we're going to square it. Now this is where maybe it helps to kind of write it out and try not to do it all in your head. But we're going to do 3y squared squared. All right, so what does that mean? That means 3 squared, and that also means y squared squared. I know that sounds wrong, but I'm saying it right. So 3 squared is 9, and y squared squared is y to the 4th. So this is going to be 9y to the 4th. And that's it. This is completely, absolutely 100% factored. There's nothing else we can do with that. So I'm going to do the cube root of m cubed. Now the cube root of m cubed is going to be m. And then we're going to do the cube root of 64 p to the 15th. Well, the cube root of 64 is going to be 4. 4 times 4 times 4 is 64. And then when it comes to the exponent, we're going to divide by 3. So the cube root of p to the 15th is going to be p to the 5th. So that's how you do that. All right, so I wrote out the format there. Now this is a sum of 2 cubes, so I wrote plus here, and then there's a minus there. So now I'm just going to put the a and b, I'm going to put the values that represent a and b in their proper spots. So a is m, and b is 4p to the 5th. So there's your binomial. And a is squared, so we're going to put m squared, because that's what a is m. minus the product of a and b. So now we're just going to put it all together. So I'm going to put 4np to the fifth, and then we're going to do b squared. So we have to do 4p to the fifth squared. Now 4p to the fifth means 4 squared times p to the fifth squared. Now 4 squared is 16. P to the fifth squared, now that's a power to a power. So that's going to be p to the 10th. Not p to the 7th, but p to the 10th. So you're going to put 16 p to the 10th. And as far as we can go, that's it. Now why don't you try the next one for part D. Why don't you try that on your own just to see how your answer matches up with mine. So this is a good point where you can pause the video, try it, see if everything checks out. Again, don't stop here because the next example I want to do with you because it's a little bit different from what we have been doing. All right, guys, so that's what I got. I got 5a to the fourth minus 2b. That's your first binomial. Keep that in parentheses. And then the trinomial is going to be 25a to the eighth, 10a to the fourth b plus 4b squared. All right, so hopefully that matches my answer. Or if it doesn't, I made a mistake, I guess. And you guys probably caught it, like usual. Now, right here for example E, what I want you guys to notice here is that 16 as well as 250, those are not perfect cubes. There's nothing, there's nothing times itself 3 times that equals 16. Same thing with 250. There's nothing times itself that equals 250. And I haven't really addressed this. We haven't addressed this because we haven't had an example like this. But for this particular one right here, this one involves a little bit of factoring. Is there a GCF? And the answer to that is yes. There's a GCF that we can take out of that. So the GCF that we can remove from that is going to be what? What number goes into 16 and 250? What do you think? Well, it's not a huge GCF really. It's just 2. So we're going to take the 2 out, and then we're going to see what we're left with. Now 16 divided by 2 is 8. The x cubed is not affected by that. And then 250 divided by 2 is 125. And then you'll notice what we're left with now are perfect cubes. 8 is a perfect cube as well as 125. And that was the goal. All right, so if you're ever stuck with these, maybe look at whether or not they're perfect cubes to begin with, and maybe you can factor something out so that you have perfect cubes that can factor. So now I'm just going to take the cube root. Now, I'm not going to forget about that 2 as well. Just kind of hold on to that 2 for right now. And sometimes I do forget about it, but let's kind of just hold on to that. I'm going to take the cube root of 8x cubed. And what do we get when we do that? We're going to get 2x. 2 times 2 times 2 is 8. X times x times x is x cubed. And then I'm going to do the cube root of 125, and that's an easy one. That is going to be 5. 5 times 5 times 5 is not 15. 5 times 5 times 5 is 125. You know that, right? And just like I've been doing all along, I'm going to write out the format for, and this is a sum of 2 cubes, so sum of 2 cubes is going to be a plus b. And then I'm going to kind of put that 2 out in front, because just because we factored out that 2 doesn't mean it's like gone. It's still part of the factorization there. It's now not inside the parentheses. It's outside the parentheses. It's being multiplied, but it's still a valuable factor in all of this. So a and b, a plus b is going to be 2x plus 5. A squared is going to be 2x squared. Well, 2x squared means 2 squared times x squared, which is 4x squared, minus the product of a and b. Well, the product of 2x and 5 is going to be 10x, plus b squared. That's going to be 5 squared. So 5 squared is not 10. 5 squared is 25. And as of right now, we are through with this problem. And that's all you get there. And so that is factored completely. And that's really the goal for these problems. I know we didn't get like a nice succinct answer like 5 or g squared or something like that. We've got a problem that looks like more math needs to be done, which is indeed true. But in terms of the factoring, and that was our goal, that was our objective, we're done. We're through with that problem. Okay, so that does it for your lesson. This was probably definitely, absolutely 100% brand new to you. So if you need to go through it, ask questions, let me know. And we might spend another day practicing this just so that we can get it down. Hopefully this made some sense to you and we did enough examples. And of course, let me know if you have any questions. All right, so everyone have a great day. See you later.